uh, in search of the Holy Grail. I think everyone is searching for the simple wire antenna that's low cost, easy to build, easy to deploy, with great performance from a single band to multi-band. And everybody's searching for that. And the end-fed half-wave antenna comes close, comes very close. A fundamental thing that we all have to consider is, where are you using it? It's really operation dependent. Is it for home use, where you have a semi-permanent installation, plenty of real estate and mounting options? Field day, you got to deploy it pretty quickly. Mounting provisions may be limited. You may have co-located setups which interfere with each other. Parks on the air, you need something for very quick deployment, portable and lightweight, with limited mounting provisions. Summits on the air is even worse in that regard. And DXpeditions, you want good performing antennas with moderately quick deployment. You have a little bit of time to set up, easily transportable. So one antenna does not fit all. You have to choose the right antenna for the application. So end-fed half waves, what advantages do they have compared to other wire antennas? Very easy to install. Only a single high point is required, like a single pole or a high tree branch. Makes a great field antenna with quick setup. It has lots of configurations possible. It could be a horizontal, like a dipole, or an inverted V, an inverted L, a sloper, an inverted U to take up less space, a half square, which will have gain on the on certain bands, etc. Big advantage is there's no hanging feed line, like a dipole or an off-center fed dipole. The feed point could be near the ground too. It doesn't have to be way up in the air. You need a minimal ground system or counterpoise. Even the coax feed itself can serve as a counterpoise, with or without a choke balance. It's resonant on many bands with low VSWR, and almost every other antenna can't make that claim. 80, 40, 30, 20, 17, 15, 12, and 10 with low VSWR. At worst, you may need just a 3-to-1 touch-up type tuner, which is built into most modern rigs these days. Because you have low VSWR, you have reduced coax losses as a result. It's pretty easy to adjust the length. One length adjustment sets all the bands. There's no interactions like in a fan dipole, for example. It's inherently grounded at DC through the transformer, so there's no static buildup. And shortened versions are possible in a limited area, and I'll talk about those later. Okay, about half-wave antennas. A half-wave is a resonant radiating element with an electrical length of a half wavelength. Total length in feet is roughly 468 divided by the frequency in megahertz. But its feed point affects its impedance. It has high current, low voltage at the center, and just the opposite at the ends, low current, high voltage. The most common half-wave antenna is a dipole. Its impedance is about 72 ohms. It's basically a monoband antenna, although you can use it on the third harmonic. For example, a 40-meter dipole could be used on 15 if you tune the 40-meter and way at the low end, and then 15 meters will be at the high end. And there's some tricks to make both resonant, but I'm not going to discuss those now. It's a pretty limited antenna, as long as you're happy with a single wavelength primarily. If fed off-center, for example, let's feed it at the 29.7% point on 80 meters. Its feed point will be about 200 ohms, and it can be used on multiple bands. It will need a matching device, such as what's known as a 4-to-1 impedance hybrid balun, which consists of a 4-to-1 Ruthroff balun cascaded with a 1-to-1 Guanella balun or choke balun. If fed at one end, such as the end-fed half wave, impedance is in the 2,000 to 4,000 ohm range. So it's going to require a high impedance matching device, such as a 49-to-1 impedance transformer or a tapped parallel resonant circuit, also known as a Fuchs antenna tuner. Here's why multiband operation works with a half-wave antenna. If you start off with 80 meters, let's say 3.57 megahertz, and multiply it by 1, 2, 3, 4, 5, etc. through 8, you'll notice that you have a resonance point on all bands. So that's really wonderful. Now that's in the ideal case. Now, depending on the way you feed it, things change a bit. If you're on the fundamental frequency, let's say you're on 80 meters with an 80-meter half-wave antenna, the radiation pattern will be identical no matter where you feed it. But when you operate on higher bands, the radiation patterns will be different depending on where you feed it. You'll have more and more lobes as you go up in frequency, but the lobes will change their positions based on where you feed the antenna. That's a key characteristic of these type single wire antennas. The feed point location does affect the radiation pattern on the harmonics, though identical on the fundamental. Now, here's a sort of a picture of an unknown transformer for end-fed half-wave antennas. The one on the left is the classical transformer. This one shows a 2-turn primary and a 14-turn secondary. And there's a couple of wires twisted together between primary and secondary. And you'll notice also it has a crossover. That crossover is primarily for mechanical reasons. It lets you put the output of the transformer up near the top. So it's more for mechanical convenience than any other reason. It does affect performance a bit, but not very much if you wound it continuously. The other option is a auto transformer, which is also 2 turns to 14 turns, but you're tapping into the second turn instead of using a twisted pair, as in the first example. Now, both of these typically will require what's known as a compensation capacitor, goes across the primary. And what that does is it makes the high frequency response improved when you have that. Most commercial ones do have that compensation capacitor in them. Here's sort of a block diagram of an end-fed half-wave antenna, and some of the blocks are optional. The rig typically will feed coax into a unknown transformer and go up to the antenna. That's its simplest form. In that case, the coax serves as the counterpoise. Now, you could get fancy and put a choke balun in here in the middle of the coax, and the short section of coax between the choke balun and the unend can act as the counterpoise. Typically, it's 0.05 wavelength long at the lowest frequency of operation. That makes it non-resonant on all the bands, so you don't end up with a half wave on any band, which would be a high impedance and not work very well. Now, I show a compensation coil here. The purpose of that is to make the resonances line up a little bit better on all the bands, because you have what's called an end effect on the lowest frequency of operation. The antenna tends to be shorter than what you would expect. So because it's shorter, if you do nothing else, the higher resonances will be too high, because the end effect gets smaller and smaller and smaller as you go up in harmonic frequencies. So you could compensate for that by putting in a little coil of wire. My antennas uses that in their antennas, and a lot of people copy that idea and use it on theirs. Another thing you can do is, if the 80-meter wire ends up at the low end of the band, and maybe you're a sideband operator, you can do another trick, which is to put a capacitor in the center of the antenna, the electrical center. And that capacitor will raise the frequency of the 80-meter segment and have almost no effect on the higher bands. So by doing that, you effectively can move around the 80-meter resonance point anywhere you want. This could be like 250 to 500 picofarads on that order. Now that will need a bleeder resistor across it to bleed off static charge. Counterpoise. Now counterpoise is a very controversial subject on the Facebook groups. The point of it is current that's flowing into the antenna's driven end must be equaled by the same amount of current flowing into a ground or counterpoise of some type. That's just how antennas work. If you don't specifically provide a counterpoise, then the coax shield will be a counterpoise. And people use it that way. In fact, at home, I just use coax with no special counterpoises or transformers or anything. The antennas are very far away from the operating location, so I don't have any problems with common mode stuff and RF getting into everything. But some people do have problems with it. So you could use a counterpoise. Now, in reality, what happens is current will flow on the counterpoise, but some current will still flow on the coax, feeding the unknown, and they split up. If you have a good counterpoise and a choke, you're pretty much isolating the counterpoise current, and it doesn't get onto the feed line going into the shack. The ideal length of a counterpoise would be a quarter wavelength. That would be a low impedance, but that's only good on one frequency. But you don't want it to be a half wavelength long. That's a high impedance, and the counterpoise wouldn't do much. So what's worked in practice is to make the counterpoise 0.05 wavelengths long at the lowest frequency of operation. That's about 13.2 feet on 80 meters and about 6.6 feet on 40 meters. And that's non-resonant on all bands, but it works pretty decently. You could also look at your particular location. If there's a wire fence nearby, connect to that. It makes a great counterpoise. If you have a good radial system, that'll make a great counterpoise too. Maybe you have one for a vertical or something, tap into that. So there's flexibility in how you implement the counterpoise. Is a choke balun needed? Well, depending on the quality of your counterpoise, as I said, current splits between the counterpoise and coax shield. So a choke balun will help minimize stray RF getting into the shack, but you could often get away without one. You could either put it right at the rig, or you could put it in series with the coax, 0.05 wavelength away from the unknown, and then that acts like a counterpoise. If you want to make a high power choke balun, my go-to balun is an FT240-31 with 12 turns of RG 400 coax. That'll take high power, and it has good choking ability for 80 meters and up. Now let's touch on ferrite materials. If you look at all the commercial antennas around, most of the ferrite materials used are what's called type 43 or type 52. Type 43 has a pretty high permeability. It's medium cost. It has a relatively low Curie temperature. Curie temperature is the temperature at which the ferrite stops acting like an inductor and acts like a stick of wood. It doesn't work. If a toroid is overheated, when it cools down, it'll start working again. So type 43 is good for low cost or 100-watt rigs. The next one up is the type 52 ferrite. It has a lower permeability, a little bit higher cost than the type 43, lower losses, and it has a very high Curie temperature of 250 degrees. So it's good for high power applications because it'll take more temperature abuse, but you don't want it to get too hot because the case may start melting way before you reach the Curie temperature. Then there's something called type 61 material. That is generally not recommended for end-fed half-wave transformers because the permeability is very low, and you will probably not have adequate inductance with standard materials. So I would stay away from it unless you really, really know what you're doing and you're limiting how many bands you operate on. I actually made some 61 unknowns that work, but it took a lot of work to make it work. And it's not for the casual builder. So stick with 43 or 52 and you will do okay. If you look at data sheets on ferrites, it looks like this picture on the bottom. There's something called U prime, and there's something called U prime prime. U prime represents the inductive component of the permeability, and U prime prime represents the lossy component. Permeability is actually complex. It has a real part and a inductive part. And never ever use iron powder cores for end-fed half-wave unknowns. They have even lower permeability than the type 61. So they just don't work at all. Never use iron type cores, powdered iron, for end-fed half-wave unknowns. Compensation capacitor, what does that do? When I first started learning about these things, I had no idea what that's doing at all. It seemed like magic to me. And I learned fairly recently that the way it works, it's acting like a lumped element approximation of a 50 ohm transmission line in conjunction with any leakage inductances in the transformer. These transformers typically have leakage inductance, which at high frequencies looks like a series L driving 50 ohms. The load impedance gets reflected back to the primary and looks like 50 ohms. So it's a series L shunt C. It's a low pass filter. That's going to degrade the high frequency performance. But with a compensation capacitor, you're making a lumped element approximation to a transmission line. So it improves the high frequency performance by changing the series inductance to something approaching a transmission line, and hence correcting for the leakage inductance. Now, the capacitor itself, a lot of people buy these blue capacitors on eBay, high voltage capacitors. They want 5 kilovolts, 10 kilovolts, etc. That's really not the way you want to do it. Luckily, most of those capacitors work because they have relatively high current capability. What you really want is a low equivalent series resistance capacitor. Not too many have that rating, but I listed one here, a particular KEMET capacitor. It's rated at 3 kilovolts. It's rated for low ESR, and it costs $2.41, which is not horrible, but it's not trivial. But that will work in 100-watt rigs and probably in higher power rigs as well. For 100 watts, you only get about 446 volts across the capacitor with derating. With 1,000 watts, you get about 1.4 kilovolts. So you don't need 5 kilovolts and 10 kilovolts. You really need low ESR. That's the key thing with these compensation capacitors. Now, let's talk about a compensation coil. Some of the commercial antennas, like my antennas, have that magic little coil to help correct the resonance points on the higher bands. If you want to make your own, it's about 1.5 microhenries, 6 turns on a 1 1/4 inch outer diameter PVC form, positioned about 78 inches from the feed point, whether it's 80 meters or 40 meters. Steve Ellington, who used to run a Facebook group called end-fed half-wave antennas, has a YouTube video on that topic if you want to take a look at that. And this is what he measured. Excuse me. 80 through 10, that's about how many kilohertz the resonance gets lowered. So that works out pretty well. Now let's take a look at another topic here. And there's always a lot of confusion about this. How does an NFET half-wave transformer behave with a resistive load versus a rail antenna? And I try to show a picture on the left side. This is what the SWR as a function of frequency looks like from 3.5 to 30 megahertz. It doesn't always look like this. Sometimes it'll gradually slope up. Sometimes you could actually get two dips, all kind of dipsy-doos over there. So it really depends on the toroid or toroid stack, the material, how it's wound, the size of the toroids, etc. So the shape of this will vary quite a bit. But with the correct compensation capacitor, the SWR will go down over most of the band. So it's very helpful to have one. Now, surprisingly, when you use a rail antenna on the transformer, the SWRs can actually be lower than what you get driving a resistor. Why is that, you ask? And I always wondered about that. Well, again, you have leakage inductances. So at the high frequency end, it looks like a series L shunt R low pass filter. But an antenna at its resonant frequency looks like a series RLC. And if the antenna is too short, it will look capacitive. It'll look like a capacitor in series with a resistor. The capacitive reactance cancels out some of the inductive reactance and makes it look better. So the SWR with a rail antenna could actually be significantly lower than what it looks like with a resistive load at the high end. Thought that was kind of cool. Now, if I talked about this earlier, if the 80-meter resonant point is too low, you can raise it by putting a capacitor in the middle of the wire. And Steve Ellington did a YouTube video on that, which is very informative. Okay, what happens if you don't have enough room for a full-length horizontal antenna or even a sloper? You can shorten it by using an inductance in series with the wire. This is one version for 40, 20, and 10. Another version for an 80-meter one that covers 80, 40, 20, 50, and 10. This will let you shorten the antenna by somewhat better than 2/3 of the normal length. And it works. People have built these and they work. The only disadvantage of them is that you have a little bit of loss in the inductors and the bandwidth is narrower. You will not get the full bandwidth you get with a full-length antenna, but it's a way to make an antenna where you don't have the space. Well, you also use an inverted L. That's another technique where you could make an inverted U, which will save some horizontal space as well with a full-length antenna. Adding 160-meter capability. Well, an 80-meter half wave is actually 160-meter quarter wave. So as long as you have some sort of radials or ground system and you have a way of switching out the transformer, then you'll have a quarter wave on 160 meters. And Steve Ellington expanded on that concept in another YouTube video that you can watch. You need to basically disconnect the antenna from the unon and connect it directly to the output of the coax. But you do need some sort of decent counterpoise system or ground radials for that to work decently. Okay, air venting the housing. I think when these things first started off by the commercial people, they just drilled 2 holes in the bottom of the housing. And that's how I built mine, and it seems to work okay. But some of them now are selling them with air vents to let out moisture and equalize pressure. And that works, but they're fairly pricey. They're about $4. So if you want to get fancy and use a real air vent that also is a pressure relief valve, the air vent is a good way to go. Now, this next slide to me was very key. The importance of primary inductance on end-fed half-wave transformers. These things are very high turns ratio, and as a result, you'll get leakage inductance very easily. Unlike, say, a Ruthroff balun, which is only a 2-to-1 balun, and it's based on transmission line transformers. The end-fed half-wave transformer has such a high turns ratio that you can't use a transmission line transformer for it. It's more of a conventional transformer, and it suffers from leakage inductance, which degrades the high end. But if the primary inductance is too small at the low end, you'll get a mismatch loss. The equivalent circuit will look like a shunt inductor and 50 ohms, and you're feeding that with a 50 ohm source. So the inductive reactance, if it's too small, it will low down the circuit and cause the VSWR to climb. If the primary inductance is too high, you won't have the low end problem anymore, but you'll have the low pass filter effect at the high end. So the high end performance will suffer. So there's a happy medium on what the inductance should be at the primary, and you want it in the 88 to 200 ohm range at the lowest frequency of operation. And this corresponds to about 4 to 9 microhenries on 80 meters, or 2 to 4.5 microhenries on 40 meters. Now, inductance varies with the size of the toroids. Bigger toroids have higher inductance for the same number of turns. Or if you stack toroids, that increases the inductance by how many toroids you have in the stack. So if one toroid has, say, 4 microhenries of primary inductance, 2 toroids will have about 8 microhenries. You can compute that value very easily by going on this website, toroids.info. You could put in the type of toroid you have, number of turns, and it will compute the inductance value for you, and you can see where it stands. That's a real useful site to get a quick estimate of inductance. And if you have 2 of them, just take that value and multiply it by 2. Or if you have 3 of them, take that value and multiply it by 3. And that gives you a primary inductance. Now, this next chart I thought might be useful to have in here. There's a lot of arm waving on how big toroids have to be to handle a certain amount of power. And there's this fellow, Owen Duffy, at owenduffy.net, and he has all kinds of calculators. If you want to see all his calculators, it's owenduffy.net/software. And he has a temperature calculator that basically takes the surface area of a toroid or toroid stack, and you tell it how much temperature rise can you tolerate, and it'll compute how much dissipation the toroid can take. Well, conversely, if you tell it how much power the toroid dissipates, it'll tell you what the temperature rise will be. So I took a bunch of commonly used toroids, and I computed how much power they would dissipate based on their surface area if you let them rise to about 150 degrees Fahrenheit, assuming a 25 degrees C room temperature type starting point. And you could use this chart by putting in your own efficiencies for anything. Like if you have a Ruthroff balun and say it's 98% efficient, you can compute all these numbers based on that. These numbers are mid-band representative numbers for an end-fed half-wave transformer. And these percentage is shown are pretty poor in some cases. 85% efficiency is not very good. It's not horrible, but it's not very good. 90% and up is very good. So if you take the efficiency, you could compute 100% duty cycle powers, or for CW, assuming a 44% duty factor, you can compute those. Or for sideband, assuming a 20% duty cycle, you could compute those. So a classical unknown uses two FT240 43s, and that can dissipate close to the full 100-watt limit, 200 watts or so on CW and about 450 watts on sideband. If you want a high power one, use type 52 material. It'll give you more of a safety margin and temperature rise. And those are more like 90% efficiency at midband, 14 megahertz, say. And on sideband, they'll dissipate up to 900 watts. One that I like, I called it the stubby because it's sort of short and chunky. That's a single transformer toroid, which costs about the same as one FT240 43. And it will make a transformer that's 90% efficient. And it could dissipate more than enough on CW, 159 watts and 350 watts on sideband. So it's pretty good and pretty efficient. And here's a picture of that that stubby transformer. You'll notice it has a smaller inner diameter, like the FT140s and FT240 type things. They're more skinny. This is more, has a larger cross section, which makes it very efficient as far as its magnetic path. There's something called sigma A over L or sigma L over A, which you can find in data sheets. And if it has a good number, it means you need less turns to get the same amount of inductance. And this has been built by a few people. In fact, in one of the Facebook groups, the guy that runs my antennas, he himself said that's a good toroid if you want to make your own homemade unknown transformer. Now here's a list of common errors, and I've seen these all the time, people posting on the various Facebook groups. Using the wrong material. Don't use type 61. Don't use powdered iron cores. Use 43 or 52. Don't put insulating tape on toroids. These toroids, these ferrites, have a high resistivity. You're not going to short out anything. If you put tape under them, it increases leakage inductance, which you don't want to do. So just wind the wire right on the toroid directly. And it takes high power and it's fine. People count wrong number of turns. A turn going through a toroid is something that passes through the inside hole. That's one turn. Even the crossover turn is one turn if you have a crossover. Another mistake is how you run the wire. Don't run it next to any metal, like a tower. Especially the high voltage end, right where it comes out of the unknown. That's very sensitive to nearby objects, so try to keep that pretty far away from metal. like at least I'd say 5 feet or more away. 10 feet would be better. Another mistake people make is trying to use a choke balance but putting it right next to the on. When you do that, you have no counterpoise anymore. So it's going to find a way to make a counterpoise, and it's going to basically use your coax feed. So it'll work, but you'll end up with a high common mode current on your coax feed. Then there's a lot of confusion about turns. Like there's 4-to-1 transformers, and there's 9-to-1, and there's 49-to-1. So what you need for an end-fed half wave is 49-to-1. 4-to-1s are generally used for Ruthroff balance. 9-to-1s are generally used to match random length antennas. So people get confused about what kind of transformer is needed for end-fed half waves. You really want a 49-to-1 or a 64-to-1 ratio, high impedance ratio. And then here's a big one on the bottom: putting too much power in an undersized unknown. And people do this all the time. And what happens is they just overheat, and then they wonder why the SWR climbs. The SWR climbs because they reach the Curie temperature, and there's no longer any inductance in the core. It acts like a piece of wood, like I like to say. And it doesn't act like a transformer anymore. But after they cool down, they usually recover. Also, they could melt the plastic case. They get really hot. If it's hot enough to reach the Curie temperature, you're way above boiling water, and you're going to damage the case. So use that size chart that I showed, and you'll be in the right ballpark for how big it has to be for how much power you plan to run. Recommended antennas and unknown vendors. For 100 watts and up, I recommend my antennas. Daniel Horvat, I think his name is. He knows what he's doing. So I listed here a couple of transformers. If you want to save a little money and use your own wire, you could buy ready-made complete antennas also. And his power numbers are legitimate, and his transformers are very efficient. So he knows what he's doing. I would not recommend Ballon Designs for these type transformers. I bought 2 of them from Ballon Designs, and he has good quality materials, very good quality, very good construction, but he doesn't know how to make end-fed half-wave transformers. He makes good choke balance, very good choke balance, but not end-fed half-wave transformers. And for QRP, I'd recommend stuff that QRP Guys has. They do make a 40-to-15 mini tuner, which is a Fuchs type tuner, parallel resonant circuit with a tab, plus a N7VE type Viswa bridge, which lets you feed into a partially resistive dummy load while you're tuning up the antenna, and then switch over to normal operation for the full antenna. There's a YouTube review on it, and it's fairly inexpensive for what you get. It works well and has the tuner built in. Now here's some thoughts on the ARRL end-fed half-wave kit. Kudos to the ARRL for promoting this type of kit. It was very popular. It was designed by this company, High Frequency Kits, HF Kits. It's designed for 40 through 10 meters. The transformer is not designed for 80, only for 40 through 10. They rate it as 250 watts PEP. Good quality parts, good instructions, easy to build. I know some people that have built it, and they said that the instructions are very good. The little problem with it, though, is it's fairly inefficient, especially at the high frequency end. It has about a 1 dB loss at mid-band. It's about 80% efficient, and 1.5 dB loss on 10 meters, which is about 71% efficient. If you want to build one, I would recommend just purchasing a second FT240-43 so that you have two of them instead of one. You'll have lower losses, as well as whatever power is left that you have to dissipate, it's split among two toroids instead of one. So they run a lot cooler. The SWR will go up a bit with the two toroids compared to one because they're lower loss. The lossiness of the single toroid makes the SWR look better than it might look if you had a more efficient transformer. So I would do that if you want to build one. You may have to provide your own wire for winding the toroids because it probably won't be long enough. Now, some people might be considering an off-center fed dipole rather than end-fed half-wave. And I'm a big fan of off-center fed dipoles because their transformers are more efficient. The transmission line transformers. So they'll run more efficient. They can handle more power for the same size toroids. And it's very easy to build a high power one. They also have less RFI issues. The main disadvantage is coax is hanging off the middle of them or offset a little bit. So it limits you as to mounting installations. Also, the transformers are very hard to come by for good working transformers. The choke portion of a hybrid balun for those has to have really good choking impedance. Otherwise, the feed line will radiate. It will cause the resonant points to shift, and all kind of bad stuff happens. But a lot of commercial places sell those transformers that just don't perform well. And I'm a big advocate of building your own. So the end-fed, its big advantage is flexible mounting provisions and good low SWR on all the bands. I forgot to mention the off-center fed. It's actually not quite as good as the end-fed on operating on all the different frequencies. Depending on where the feed point is, you'll cover most of the frequencies, but not all. Some of them will have pretty high SWR. The end-fed half-wave has better low SWR on all the bands. And I have a chart here for sources of materials. The main part you need to get is the toroids. You can get those from Arrow, Mauser, DigJaKey, Kits and Parts. It's now back in business. Amazon has good quality enamel wire, Temco or Essex. Home Depot and Lowe's have various stainless steel hardware. Junction boxes. I think the Carlon one is only available now from Home Depot. I think Lowe's has an equivalent, but it's not Carlon. And you could buy other little bits and pieces of saddle type mounts to hold the various holders, etc. High voltage caps, you can get them on Mauser or DigJaKey or eBay. And you could put a wire rope thimble up on top to hold the wire on the stainless steel bolt, high bolt. And then I have some resource links at the end. I believe Anthony has a copy of the presentation. So if anyone needs it, I guess you could get a copy from him or email me at K1RF@ARRL.net, and I'll be happy to send it to you. Any questions, comments?
First of all, Steve, thank you very much. And I do have the PDF for your presentation, so I'll make that available to all the club members that are interested. And we probably will be building one of these as a project in January of this year. So I'll open up the questions from the floor first. Go ahead, Jim.
Steve, I have a couple of questions. Can you hear me okay?
Yes,
One of the, I don't want to say which dealer, but one of the dealers that sells the pre-made NFEDs has a statement in their description that says that the NFED will perform at about 70% of what a dipole would do. Is that really an accurate representation? I've used
That's a-
NFED.
that's a meaningless statement, honestly. I would say if you looked at the fundamental frequency, an NFED will have a radiation pattern identical to a dipole. You will have losses in the transformer. So if you have a pretty lossy transformer, then the power reaching the antenna will be 70% as good. But for all practical purposes, on the fundamental, a dipole and an NFED half wave will be virtually identical as far as their antenna patterns. Does that answer your question?
Part of the reason I asked the question, I don't have up an NFED at my house, but I have used a number of them for POTA type use. And I've compared it to dipoles when I've set up POTA, and I really couldn't tell the difference. I mean, I've made about the same ease of contacts with one or the other. So I wasn't sure if that was really an accurate statement.
Yeah,
The
they
other
would
thing
be,
is if I install one at my house, where I would have to install it, the coax would not be 5 or 10 feet away from my siding. And my siding is steel siding. Would that cause a problem for me? It would probably only be about 6 inches away from the siding.
I'd say try it and see what happens. 6 inches, you don't want the high voltage ends to be near the metal. 6 inches is a little bit too close. Maybe you could rig up a little pole or something to keep it away from the metal. A little, like I don't know, like 2 feet away or something like that. But 6 inches away, you're asking for trouble.
Steve, are you referring to the end of the antenna or the coax?
The ends of the NFED.
So
The
the
coax
end of
coax could run near the metal. That's fine.
Okay, it's the coax that I'm talking about, I was anticipating I was probably going to use that as a counterpoise and not add another counterpoise.
That would be fine. In fact,
Speed line for the installation I have in mind is going to run about 50 feet.
okay. Yeah,
So
that the coax
what I-
running.
Would be sufficient for counterpoise.
Yeah. I mean, and try it. If you do have any RFI problems in your shack, you could add a choke balun right next to your rig, and that would help.
I've already got one rigged up. I was anticipating doing that. I have had a few times when I operated portable with an NFED, and I did have some problems, not with sideband or CW operation, but when I did digital operation, I did have problems with current getting back and making the computer go crazy.
Yeah, I mean, your best bet there, but it'll take more work, is you could put a choke balun 0.05 wavelengths around away from the transformer, and then run the coax from there back to your shack, and you could put a second one if you had to right at the rig, so you have 2 of them, and that should totally kill any interference. But it's more work, using 2 transformers.
Thank you for your presentation, Steve.
You're quite welcome.
Other questions? Of the
Look, if you look at the resource links at the end, I put other presentations there. I have one on doublets, and I have one on off-center fed dipoles. So you might want to take a look at those. Any other questions?
Go ahead, Frank.
Steve, earlier in your presentation, you mentioned using an 80-meter NFED as a 160-meter, requiring quite a bit of counterpoise. Does that then become basically a center-fed 160-meter antenna, basically a dipole?
No, it's more like a quarter wave vertical or a quarter wave, it depends on how it's laid out. If you have a sloper, it's more of a quarter wave antenna laying on its side. But
Okay,
on 160 meters, the antenna is going to be so close to the ground anyway that the radiation pattern is just going to be a big blob. It'll be a great NVIS antenna,
okay,
but it's really like a quarter wave vertical or a quarter wave vertical laying on its side or in an L shape.
okay.
Any other questions?
Steve, when it comes to winding the coil, is the gauge of the wire important? And does it have to be enameled wire?
It should be enameled wire, so it's pretty close to the cores. I think when some people first started winding these things, they would use number 12 wire. Unless you're running high power, you don't need number 12. You could use, like for a 100-watt rig, number 16 is fine. You could use 14 if you want. It's much easier to bend than 16, but 16 would be okay also for 100-watt rigs. And for like up to say 500 watts or so, you could probably use number 14 and you'd be okay.
Okay, thank you, Steve.
Okay.
Go ahead and see if there's anyone on Zoom that has questions. If you could unmute if you have questions. Okay, I don't hear anyone on Zoom. Anyone else in the room have questions? I had a question real quick. On the wire that you're using to wrap the coil, it's only for power purposes. It has nothing to do with the inductance or anything that's created, correct?
Well, it's part of the transformer, but I've gone through calculations on what the power dissipation is on the wire versus what the power dissipation is in toroids. And by and large, all the power dissipation is in the toroids. There's very little in the wire, even taking into account all the fancy losses in a wire. It's still only a tiny fraction of what's dissipated in the toroids. So I wouldn't worry about it.
Any other questions? Thank you very much, Steve. We will
Okey-dokey.
be sharing I'll be sharing all the resources you provided with us with the club, and we'll get back to you when we get our project planned out. We may ask you to take a look at our final plans if you don't mind.
Absolutely, no problem at all. I enjoy doing that.
Well, 73.
Okay, 73 all. Have a good rest of your evening.
Thank you.
Okay, take care. Let me see if I could
You have a good evening.
see if I could unshare. I'm not sure. I have the Zoom thing shrunken down here.
I can stop your sharing for you.
Yeah,
No
could you do
problem.
that, please?
Yes.
Okay, so I see it. Stop share. Okay. All right then.
Thank you very much.
My pleasure. Have a good evening all. Okay, I'm going to leave.
Okay, we'll see you.
Okay,
We'll
take
go
care.
with announcements, and if you could give your name and call sign and maybe where you're located. So I'll start. I'm Anthony KZT. I'm located in, and the announcements I have this weekend is the CQ Worldwide Single Sideband Contest. It's the biggest DX phone contest of the year. The exchange is very simple. Our exchange is 594 because we're in zone 4. If you're not interested in submitting a log for the contest, you don't need to worry about it. You can just work the stations and not even worry about what exchange they give you, but be able to give them a 594 exchange, so they'll be happy on their side. It's DX only, so you don't want to call US stations, but you can call Canadian stations or anyone outside the US, including the US territories of Puerto Rico, Hawaii, Hawaii counts separately and Alaska counts separately also, so they're not part of that. The November 4th and 5th will be the AWRL sweepstakes. That's a domestic contest working US stations. That is the CW version on that weekend, and then 2 weekends later is the phone version of the sweepstakes, and the exchange for that is rather complicated. It's a serial number, so you start at 1 and you move up each time. It's a single letter designator, depending on whether you're running 100 watts, 1,000 watts, whether you're a multi-operator, a university, or school, or QRP. Then you have to give your call sign, the last 2 digits of the year you were licensed, and the section, which will be Ohio. So if you're interested in operating those contests, those are coming up in November. And then Thanksgiving weekend is the CQ Worldwide CW contest. And then the other 3 contests in the year are in December. The AWRL 160 contest is the first weekend in December. It's a CW only contest though. The 10-meter contest is the following weekend, and it's a phone or CW contest, and it's great for text. 10 meters should be open, so put that on your calendar. It's second weekend in December, and the exchange for that is your section, which is the Ohio. And then finishing up the year is another 160 CW only contest, and that's the Stu Perry contest. It'll be between Christmas and Thanksgiving, and that exchange is your grid square. Other reminder is if you have newspaper, if you have newsletter articles, please get them into Vince by the end of the week. And I think that's everything I have. Frank, why don't you go next?
Great, name is Frank Tompkins, WAZT. My only comment in general is if you're new to ham radio, the band conditions because of the solar cycle are right now favoring the higher frequency bands. If you want to do any band specific awards such as Port Dalt States on 10 or 20, now is the time to do it. Wait 5 years and you'll have to wait another 6 for the next cycle. And that's really about all I've got.
Steve, KEAYTG, I'm Stowe. I'm Jim, KC8YYS, Stowe.
Recently devoid of 2 masks.
Right.
He's maskless now.
Right.
Thank you. Donated to the club.
Thank you very much for the donation.
Thanks for taking it down.
Bruce, AKB. And I want to make sure everybody knows about the Ham Fest this weekend in Massillon on Sunday.
It's at,
Let's be a good one.
it's at the Air Museum, their maps. On, is that 241 there? Is that?
Yeah.
That's 240.
It starts at 8 a.m. to the public.
Yeah, open to the public 8 a.m. I believe 6 a.m. for setup.
You'll be there early, I won't.
Okay.
They did mention, I heard make an announcement there the other night, they did mention that, you know, the price of getting into the Ham Fest, why you can then take advantage and go through the whole Maps Museum. That costs you a little bit more than what the entrance is.
Well worth it.
My name is John, my call sign is WO3X, and I will be the net control station for the 5th Monday this month. And so the VHF UHF net is at 8:30 p.m. and then the band exploration net is at 9:30 p.m. And so we will be on 17 meters on or about 18.127 megahertz upper sideband. And so this is for us on that frequency.
It's like a blue moon if we have an extra weekend in the month, so I guess it's the blue frequency.
Yeah, blue frequency.
We'll be doing 160 come January, correct?
Yes, yeah, there's 5th Monday in January, and we will be on 160 meters at 9:30 p.m. on or about 1887 kilohertz.
Daryl,
My name's Daryl, it's Kilo Echo 8 Uniform Kilo Yankee, and I'm right here in Stowe.
Jim, WA3JAT, I'm here in Cuyahoga Falls. As you heard, I'm hoping to get another antenna up before winter.
Forrest? You want to give your call sign and introduce yourself?
I think he heard.
Of course,
Name and
introduce yourself.
Forest, 88YAX, Cuyahoga Falls.
Thank you.
Paul, KB8RWZ, I'm from California. Jeff, W8DX from Hack.
And finally, we saved the best for last.
Oh, hi, I'm Greg, W8YYS, I'm from Stowe. The only thing I have is the Summit County areas will meet on the 15th. That's the third Wednesday of the month now. And this will be our last meeting of the year. The new meetings will resume on the 15th of January, I believe. And this final meeting, there will be a refresher on FL Digi if you want to get in on that. And if you got those Linksys routers, we can flash them for you so you can get on high-speed multimedia. That's at the American Red Cross. It's 501 West Market Street. And meetings begin at 6 o'clock.
What was the date on that?
15.
15th of November, okay. And I forgot to mention, we have oops. Let's come back. We have 2 more meetings in November. And then our only December meeting will be our holiday dinner, celebrate Christmas, Thanksgiving, New Year's, all your winter holidays at one time. It'll be December 6th, starting at 6 p.m. at the New Era Cafe. That's 10, I forget the street name.
It's right there.
It's
Massillon.
Yeah, Massillon, yeah, thank you, 10 Massillon Road. Just there were 76 East Market. We'll then have order off the menu. We will have a speaker that night, Dr. Max Grubb, who's a professor at Youngstown State University and a Silver Lake resident. He'll be talking about broadcast radio and focusing on the Akron area. He did a presentation for the library and he talked about some history and some of the commercialization that goes on behind the scenes that we don't know about. That's sort of interesting. So yeah, I think he should be a good speaker and hopefully we'll have a good crowd. There'll be a link on the website tomorrow that you can sign up. We don't need you to sign up with what you're going to purchase. Just give us an idea of how many people are going to be there so we can let them know how many waitresses they're going to need for us. And then they will cut that in half. Anything from anyone on Zoom? Any announcements out there? Anyone else?
Save the camera.
Okay, can we have a motion?
Oh, yeah, have a motion to adjourn this evening.
I'll move.
Forrest and Bruce seconds. Thank you all for coming. Be safe going home, buckle up.
Appreciate a little help, wrapping up the room we had to settle and stuff.